All right, hello and welcome everyone to the spooky edition of the Automate seminar. Today we're going to talk about Do-PFN, presented by Jake and Arik, which is a great work on an interesting work on causal effect estimation, which also got a spotlight paper at NeurIPS this year. And with this, please take it away.
Yeah, cool. Thank you very much, everyone, for having us today. Arik and I are both in the beginning of our PhDs, so we're always kind of excited when people ask us to to give a talk about Do-PFN. So yeah, today we're going to be giving about a 45-minute talk on what we have been working on, which is called Do-PFN in context learning for causal effect estimation. And yeah, so I'm joined here by Arik Hoyte, who is a first-year PhD student at the University of Cambridge. And yeah, we're also speaking on behalf of a really great set of co-authors, Noah Holman, Siyuan Guo, Frank Hutte, and Bernhard Schulkopf. And yeah, as Leonard mentioned, Do-PFN will be at both NeurIPS and EURIPS this year. So yeah, I will be in Copenhagen and Arik will be in San Diego. So yeah, look forward to seeing some of you there. All right. So without any further ado, let's get into it. So the topic of today's talk is going to be, very broadly speaking, on causal interventions. So these are questions of the form, what is going to happen to this if I do this? And these interventional questions are really central to a wide variety of scientific disciplines. So you can ask questions like, what is going to be a patient's health if I give them a certain medication? Or also in the social sciences, what is going to be a person's income if I give them job training? Or you can also think about kind of population level policy decisions, right? And these interventions basically allow us to take one step past what we think of as normal prediction towards causal reasoning. So kind of making our way up the causal ladder. Right, so now I want to kind of frame to you why the answers to these questions are non-trivial. So classically and even historically speaking, these interventional questions have been answered through what are called randomized control trials. All right, so here we have kind of a silly depiction of a very specific randomized control trial where we have divided up the population into a control group and a treatment group, and basically given the treatment group a certain treatment, right? And then we want to ask for this population, what is the effect of the treatment on the treated? And the randomization in RCTs basically comes from dividing up this population in such a way that that you basically control for confounding factors, which can bias your estimate. So, although these RCTs are really robust and really reliable in terms of getting causal effects, they're really expensive and typically kind of hard to execute. In some cases, they're also unethical, so you can't just try out a life-altering surgery on people just to see what the effect is. And there are also some cases where interventions are kind of intractable, so there are some systems on which you can't intervene. So observational data is another way around. And observational data through historical studies or looking at the information of people that have come into a hospital are typically easier to obtain. And this data is really everywhere, but the causal effects in these data sources are largely untapped. The challenge with observational data is what I mentioned already in the formulation of RCTs is that they're typically heavily confounded. So when you just look at the data from a statistical perspective, it's very hard to get these causal effects, which is why we need specialized methods for it. So this is kind of the task of the field of causal inference. So causal inference asks, what is the causal effect of this on this? And to really be specific and to make sure that we don't get confused with other tasks in causal machine learning, like causal discovery, what we're really trying to estimate is these causal quantities. So one example of this is called an average treatment effect, which is a population level causal effect. And then you can also estimate what are called conditional average treatment effects, or CATEs, which are an individual level version of this causal effect conditioned on some covariates. So now that we've introduced causal inference, let's talk about how the kind of current methods for causal inference typically work. What does the workflow look like? And typically, you begin by making some assumptions about the data generating process. So here in blue, I have, well, on this slide, we are looking at several different causal scenarios, right? Where we have a treatment and an outcome, and then we have some red covariates. And one of the main assumptions that people often make in causal inference is called unconfoundedness, which is that there are no unobserved confounders in your data, and it also implies that there are no mediator variables, right? And a lot of causal inference methods require you to make this assumption, and then you can proceed forward, right? The problem with unconfoundedness that the causal ML community has started to identify is that it's a scientifically unverifiable assumption. So you can make the assumption, but you never really know whether you're correct in doing so. The other thing that I am trying to outline on this slide is that there are some cases where the causal effect of a treatment is actually identifiable, but unconfoundedness doesn't cover it, right? So there are actually cases in causal inference where the causal inference methods are kind of systematically not set up to account for them. So the goal of Do-PFN, and when Arik and I started to scope out this project, was to come up with a method for causal inference that basically works across all identifiable causal scenarios. We also want to be really upfront and say that we believe in the theory of unidentifiability. So unidentifiability is really like a mathematical concept, and we currently don't believe that we can get around it. So what we want from our model is to basically have some predictable behavior in the face of non-identifiability, right? And the general framework that inspired us was prior data fitted networks, which I assume that a lot of you are already familiar with. But tab-PFN is a specific PFN, a transformer pre-trained for the predictive task on millions of synthetic data sets that are generated from these structural causal models. This was kind of the inspiration for Do-PFN. So the research question that we asked was, can we pre-train a version of tab-PFN for causal inference? So keeping in mind the goals of Do-PFN, these two kind of desiderata that I described previously, we don't make the unconfoundedness assumption, but rather we assume that there exists a prior over structural causal models. So we kind of shift our assumptions to the prior. We then pre-train a PFN on millions of synthetic observational data sets with simulated interventions to predict interventional outcomes. Yeah, and this is kind of the big idea of Do-PFN. Now, we also want to say that there's a lot of really exciting work going on in this area. So at ICML, there were like 4 or 5 other papers, and we've also talked a lot with the authors. So we encourage you to check out also the other works in this area, because it's really quite interesting. So now Arik will take it over and talk about the methodology.
Okay, thanks a lot, Jake, for the great introduction. I will quickly also share my screen. Okay, now I would like to talk about a bit of a background on SCMs, on causality, to give a bit more of a formal explanation for some of the things Jake already mentioned. And then I will go through our methodology, which is using prior fitting for the purpose of causal effect estimation. So really, arguably the most popular and also the most commonly used formalism for causality is that of so-called structural causal models, or SCMs. So one has to say there's also alternative formulations of causality. One notable example is the Rubin's framework, which operates with potential outcomes. And actually one other related work Jake mentioned, which is called Causal PFN, operates in this framework. But we work with structural causal model. And an SCM, which is short for structural causal model, consists of 3 components. The first one being a directed acyclic graph, or DAG. And we can already go ahead and give names to all the variables, the nodes in the DAG. And each node corresponds to, in this case, a variable. And because we're really in the tabular setting, each variable really corresponds to a column in a table at the end. So that's the semantics of the nodes. And the edges correspond to causes. So there's an edge, a directed edge between, in this case, x1 and x2, because we assume that x1 causes x2. x1 is a direct cause of x2, or vice versa, x2 is an effect of x1. In this case, we have also so-called unobserved variables, which are u1 and u2. They are variables that participate in the data generating process, but we never observe them, we never measure them. So they can play the role of latent variables or perhaps also noise. And here in this simple example, x1 up to x3, they correspond to simple features. Features of covariates. T is also basically a feature. It's binary and it will have a special role later on. And Y is an outcome, and the outcome is continuous. So we task more or less with a regression task. And another component of SCMs are distributions over exogenous variables. So exogenous variables are variables without parents, which in this case is x1, u1, and u2. And we assume that there exists a distribution over them, and the distribution factorizes such that, in this case, x1, u1, and u2 are independent. That's a commonly made assumption, it's also one we make, which is that all the dependent structure comes from the structural causal. And furthermore, there are functional mechanisms or structural assignments that describe how the value of a node relates to the value of its parents, or to put it differently, how we can compute the value of a node as a function of its parents. And SCMs, now they're generative models. That's important to know. You might have seen this many times before, because that's also how TabPFN version 1 and version 2 more or less generate their data, but they're generative models. And the way we generate data from an SCM is via something called ancestral sampling, which simply means we start off with sampling all the values for the exogenous variables. In this case, we would sample the value for x1, for u2, and u1, but keep in mind u1 and u2 are unobserved, so they don't go into our table on the right-hand side. The value for x1 does. And then we can go through the graph in a topological order. And for instance, start off with computing the value of x3 as a function of x1. Then perhaps compute the value of x2 as a function of x1 and u2. Compute the value of t as a function of x3, and ultimately compute the value of y as a function of t, x3, and u2. We can do this multiple times with IID samples for exogenous noise vector, and thereby obtain a tabular data set. So where causality now, a lot of questions in causality can actually be phrased in terms of changes to this data augmentation. They can be phrased as changes or augmentations to this data generating process. So in our scenario, the data on the left-hand side was generated by an SCM, which we can denote by psi. And now we can ask questions about a slightly changed data generating process, a slightly changed SCM, which on the right-hand side is denoted by psi do t. And the difference here is that all incoming edges, which in this case is a single one, into t are removed, and t is basically treated as an exogenous variable. And the task we have now is to take data from the original left-hand side data generating process and make inference with respect to this new changed data generating process. And more precisely, we want to predict, in this case, given some values for x1, x2, and x3, and a specific value of t, the outcome y. However, the challenge is, and this is what makes it tricky, we only have data from the data generating process on the left-hand side. So you can see it in some sense as an out of domain prediction task, or task under domain shift. I think this is somewhat of a simplification, but it's I think it's a way you can think about a lot of causal questions. Motivating why this is like a causal question. I would like to explain like an example. So you can think of the data on the left-hand side as being actually patients about a medical setup. So x1, x2, x3, those variables could characterize a patient. So x1 could be the weight of the patient, x3 could be the age, and x2 could be the height of the patient. And T indicates whether the patient takes a blood pressure medication or not, and Y is then their blood pressure as a result of those factors. And on the left-hand side, H does affect whether the patient takes a medication. So you can think about, for example, older people, they're a bit more maybe in worse health overall, so they tend to be more inclined to take the medication. However, this makes estimating the true effect of the blood pressure lowering agent more difficult, because those patients, they will have a worse blood pressure to begin with, for example. So meaning that there's a confounder, which is in this case the age of the patient. On the right-hand side, this confounding factor doesn't have any effect. So you can really think about the right-hand side SCM as reflecting the RCT case that Jake also early on mentioned. So on the right-hand side, we might decide by random chance if the patient takes the treatment or not, and then we observe the outcome also given a set of covariates. And it's also important to note that this was a very medical example, and the language is very medical, but as Jake said, application of causality span basically all aspects of social and the natural sciences. One could be also a bit more precise, and if we intervene on a variable t, we denote this by do-t, which, set corresponds to independently setting t's value to small t, independent of what the other covariates do. So we can think about this as breaking all incoming edges into t, and then by propagating this change through the graph, we obtain something called the conditional interventional distribution, or CID, denoted by P of y given do t and x. And this distribution answers the question in the medical case: what is the distribution over the outcome, would be the blood pressure, assuming that I give the patient the medication while also conditioning on a bunch of covariates. So for an individual patient for which I know a bunch of covariates, I want to address the question: what will happen if I give them the treatment versus perhaps what will happen if I don't give them the treatment. CIDs immediately also allow to compute Kates, usually noted by tau of x, which are the expected difference between giving a medication versus not giving the medication. And the average of Kates averaged over all values for x, they then lead to the eighths or average treatment effects for a given population. And those CIDs, they are what we want to learn. And we do prior fitting to learn those CIDs. More specifically, for Do-PFN, we simulate pairs of observational and interventional data and put the observational data together with the interventional feature vectors into the model and teach the model to make predictions. So we can be a bit more precise. During pre-training, we first we sample millions of SCMs, and from this SCM, just as I showed before, we can obtain an observational data set. However, because we know the precise SCM, we can also simulate an intervention. And for from this intervention, we can also, from this intervened upon SCM, we can also draw data. More precisely, for the observational SCM, what we obtain is T-op, the treatment, the observational treatment version, basically X-op and Y-op. And we also obtain an interventional value for the treatment together with, more or less interventional covariates together with the interventional outcome. And now we feed everything except for the interventional outcomes to a PFN and let it predict the interventional outcome. And we do this, for millions of times. And we use this to really train our large transformer. During inference now, when you want to actually apply the model, what you need is still this observational data set. So in the medical setup, the doctor would need to have some record of patients in the past, and those patients decided for themselves if they take the medication or not. So, I mean, this is something that's possible. So this data can be confounded. This is just observational data. So right, you might say just normal data, non-RCT data. This is what we need as an input. And then for the query points, for like a new patient, potentially different features to any patient that has been observed before, we want to predict for a specific value of the treatment, which is 0 or 1, what's the expected or what's the distribution over the outcome. Now I would also like to talk about some more conceptual, some more theoretical aspects of Do-PFN. More precisely, what is a big topic in causality is unidentifiability. And Jake mentioned it already. And what the issue is, more or less, is that multiple SCMs can lead to the same observational distribution. So on the left-hand side, this SCM, we could say that's psi 0. It leads a specific distribution over a specific observational distribution. And even if you have an infinitely large sample from this observational distribution, so we know the observational distribution perfectly, we still cannot be sure which SCM might have generated this data, because multiple SCMs can induce the same observational distribution. And the class of all SCMs that are equivalent to psi 0 in terms of leading to the same distribution or observational distribution, that's noted by the term of Markov equivalence. And we use those square brackets to denote the set of all equivalent SCMs. This does become a problem when we want to estimate effects, because they will differ. So if we now want to make predictions with respect to the CID, it does depend on the SCM that generated the ground truth data, and therefore this is this is a problem, and we need to have a way out. Maybe to emphasize this once again, even if you have like an arbitrarily large sample for t, x1, x2, x3, and y, you still cannot be sure which SCM has generated it up to a Markov equivalent. So how can we get out of this? And the answer is we need to make assumptions. So we need to make some extra assumptions. And what people typically do is either assume a specific causal graph. So maybe you say, okay, I'm very sure psi 0 has generated this data. This is quite tricky to do in practice because you need to have very, very fine-grained understanding of the data generating process in order to make this assumption. People still do it. Another way out, and Jake also already mentioned this, is unconfoundedness. This relates to a statement which is basically equivalent to saying, if I know all the covariates, so all the covariates except for the treatment variable, and I condition on them, so if I know them, then my treatment assignment is basically random. To be more precise, you state that conditional on your on your x, t is independent of your outcome, more or less. This also means that there's no mediating structure. This also means that there's no unobserved confounding, which is quite tricky to justify in practice. Our assumption is quite different, and we assume that we have a prior over SCMs. So without seeing any data, we assume that there's a certain preference for specific SCMs. And this, in our case, mainly incorporates a simplicity assumption. So we assume that we prefer simpler SCMs over more complex ones. And with this prior, we always have a well-defined CID. And yeah, what we do with prior fitting is, what we can show is that we learn to approximate this the CID a bit more precisely. We can show that our model, which we denote by Q theta, when we train it on synthetic prior data, we obtain a forward Quebec Leiber optimal approximation of the conditional interventional distribution, at least in expectation over a synthetic sample. What one can also look at is what this posterior or the CID the Do-PFN approximates kind of incorporates. So as that Do-PFN learns to approximate a posterior predictive, which also has the form of P of y given x, do of t, and d op. So taking into account a new test covariate vector together with a specific intervention and all the observational data, the model makes a prediction for the outcome. And this distribution can be factorized into three components. The first one being P of y given x, do of t, and psi. So this corresponds more or less to aleatoric uncertainty. So even if we condition on a precise SCM, we still cannot be sure what the outcome will be. This incorporates uncertainty due to noise, so due to unobserved noise in the data generation process. We also have epistemic uncertainty, which is not very surprising, but what is interesting is that we also have uncertainty due to non-identifiability. So we can, from the data, we can only identify the SCM up to Markov equivalence. And then we do have uncertainty within this Markov equivalence class. And this is something our posterior also captures. And then what we can show is that what we refer to as epistemic uncertainty, so uncertainty about the Markov equivalence class, this converges to zero when we have infinitely large observational data. And we also have, in some sorts, a consistency argument saying that when we know that data come from a ground truth SCM psi zero, we convert to the ground truth posterior predictive up to Markov equivalence. So that's somewhat reassuring, but it's also only just an asymptotic argument. And now I hand over to Jake, who will also explain how our experiments back up some of those more conceptual findings.
Right, let me unmute myself. So I'm going to carry on with the experiments, which build nicely off of some of the more theoretical findings that we have. So we're going to be looking at how the model performs under identifiability and non-identifiability, do both an in distribution or in prior and out of prior analysis, and then look at how well or how surprisingly well Do-PFN transfers to real or semi-real data. So the first part of our experiments we call our causal case studies. You might recognize this slide. I used it earlier to define like the different causal scenarios that you might find yourself in when doing causal inference. We also use these to basically sample data from our prior. So we have, in this case, 6 different groups of data sets, which they all share the same graph structure. But then, of course, we vary the noise distributions and the structural equations that actually fully define the SCM. And the interesting part about these case studies, as you can see, some of them are identifiable. Some of them under some of them unconfoundedness holds. But they kind of allow us to assess the main goals of Do-PFN, which is to basically have a model that can perform well across all of the identifiable scenarios without having any knowledge of the graph or making any graph assumptions. And then we also look into what kind of behavior we have in the unobserved confounder case, where we have non-identifiability. So the first part of our results are basically evaluating 3 different causal tasks on our synthetic case studies. So in the top row, we evaluate Do-PFN in predicting the CID, which is precisely the conditional interventional distribution, which is exactly what it is trained for. And then we also evaluate it against a quite competitive set of baselines in estimating conditional average treatment effects and also average treatment effects. And we always measure some kind of error metric. On the first two, it's the MSE, and then for the average treatment effect, it's the relative error. So first, looking at the top row, what we see is that across all of our case studies, Do-PFN outperforms the standard regression models that we compare it against. Most notably, we actually outperform a model which we call Don't-PFN, which is basically a model pre-trained on our prior, but to approximate the posterior predictive distribution. And so what this tells us is that when we're talking about a causal task, so predicting the CID, optimizing for the CID actually implies something fundamentally different than optimizing for the PPD. And we also see that Do-PFN is better than tab-PFN on this data, and better than a random forest. Another reason for these results, as Arik kind of framed when he talked about the causal inference task as almost an out of distribution task or a out of domain task, is that when you predict the CID, you can sometimes induce a large distribution shift between the training set and the testing set. So, for example, you might have some data in the past about people who have taken a certain medication, and it might be that children don't actually take this medication in the real world. And then when you're estimating the CID, you might ask, what happens if a young child takes a medication? So this is a kind of a really large distribution shift in the query set. Yeah, and then in the next two rows, we see that Do-PFN performs competitively, and one could say better than a set of causal inference baselines. The caveat of these results is, of course, that these are samples from our prior, so they should be kind of taken with a grain of salt and with that in mind. But it's of course still a positive result.
I have one question, maybe, if it's okay.
Sure. Yeah.
What's the difference between the tab-PFN and the don't-PFN?
Tab-PFN, so this is the second version of tab-PFN, which is pre-trained on a much more complex prior. Don't-PFN is just using our prior. So our prior has very, very simple noise distribution and nonlinearities. So it's much more simple. Yeah. Thanks. Yes. So the next experiment that we did was basically looking at the behavior of Do-PFN under unidentifiability. And here we visualize our 6 different case studies, and the first 5, so all but the bottom right, are identifiable scenarios. And then on the bottom right, we have our unobserved confounder case study where the effect is unidentifiable. And to maybe briefly describe these plots without going into too much detail, they basically measure the correctness of the model's confidence. So we compare predictive distributions with ground truth distributions, and if the coverage is above the diagonal line, that corresponds to the model being slightly underconfident. And if the coverage is below the diagonal line, then this corresponds to the model being slightly overconfident in its predictions. And what we see, first to point out the positive result, is that Do-PFN, when you have unidentifiability, its uncertainty is correctly calibrated. So this means that it's kind of correctly confident. And we also see empirically that the uncertainty is much higher in these scenarios, which corresponds with all of the theory that we have about unidentifiability. And then the next result that we see, which is kind of either positive or you can form your own opinion, is that Do-PFN is slightly underconfident in the identifiable scenarios. And this kind of doesn't correspond to the identifiability theory, but we rather think has something to do with the bar distribution, because we do have a regression model, which might induce some approximation error, or it might have something to do with our optimization objective, but we can discuss that later. So that kind of captures the second goal of Do-PFN, which is having some predictable behavior in the case of unidentifiability. So the next thing that we do is we look within our prior. So we do what we call an in-distribution or in-prior analysis on the behavior and the performance of Do-PFN across samples of our priors with different characteristics. So on the left, we ablate over the base rate of the average treatment effect, and we see that Do-PFN is relatively robust to different base rates of the 8. We do see that it slightly diverges as we get larger base rates of the average treatment effect. This might be because in general we have more data sets with a low average treatment effect in our prior, but we see that it's much more robust than, for example, tab-PFN v2. And we think this is also connected to this distribution shift that we have when we're doing causal inference. Then moving to the right, we also see that Do-PFN, as data set size increases, performance also increases, and the model also gets more consistent. And then on the right-hand side, we ablate over graph complexity, either by the number of edges in the graph or the number of nodes in the graph, and see that Do-PFN is relatively consistent. There is some wavering, but in general, the trend is quite similar to a baseline that actually knows the causal graph. So this is kind of our gold standard baseline Do-Y. So this was also a really, really cool result. So now that we've looked within our prior, we wanted to look outside of our prior in order to kind of tease at the fact that Do-PFN can maybe be eventually used in the real world and show some transferability. So we go out of distribution in 3 different directions. So we first we vary the noise distributions that we use to sample data, and in these plots we always compare the on the left-hand side is always the IOD, which is the inside of distribution performance. And for varying the noise distribution, we see that Do-PFN is relatively robust to other distributions of noise. The only thing that causes performance to increase is by just increasing the standard deviation of additive noise, which also induces some irreducible error in the problem. So this is, I think, in general, kind of an expected outcome. We also vary the types of nonlinearities used in the structural equations. And we also see that for a lot of different nonlinearities, other than when taking the average of 2 nonlinearities, Do-PFN's performance is relatively consistent. And then we also go OOD in terms of graph size. So the original version of Do-PFN was only trained on up to 10 node graphs. And we basically see that as you increase the graph size, performance drops. As a sanity check, we also pre-train a model which we call Do-PFN v1.1, which is pre-trained on up to 60 node graphs. And we basically show here that this OOD issue can be resolved by further pre-training or more extensive pre-training. All right, so that was an OOD analysis that was, the goal was to kind of see how it transfers outside of its prior. But we also do some experiments on what we call semi-synthetic data to see how Do-PFN, although it has a relatively simple prior, how it does on more realistic data. So our first benchmark is called real cause, where we have basically it's real world RCT data, and then a corresponding observational data set is synthetically created such that it creates confounding effects of the features in the data sets. We should note that this benchmark is perfectly satisfying unconfoundedness. So all of our baselines, all of the methods that we're comparing against make this assumption in one way or another. So this is really the setting where, yeah, these other baselines are set up well to perform. But what we see is that our larger version of Do-PFN, version 1.1, performs pretty competitively with other methods, even that use tab-PFN as a base model and therefore have a really large representational capacity. We see in the critical difference plot at the very bottom that Do-PFN is really up there with meta learners that use tab-PFN or yeah. So that was kind of the setting where Do-PFN was at a bit of a disadvantage compared to the other baselines. But we also wanted to test Do-PFN on the setting for which it was designed, which are scenarios where the effect is identifiable, but unconfoundedness isn't satisfied. So we also perform an analysis on what we call our known graph case studies. So these are observational data sets where there's kind of a widely accepted causal graph. So we're not 100% sure about it, but yeah, people have kind of sat down and said that this is probably what the causal relationships look like. Then when you have the causal graph, you can fit an SCM to the observational data and then use that SCM to simulate interventions and yeah, get semi-ground truth values for Kates. And then what we see again is that actually our first version of Do-PFN, which is the model that was pre-trained on smaller graphs, performs really well in these settings, which was again, yeah, kind of surprising. But again, this is the graph scenario where Do-PFN is really designed to shine. All right, so with that, I will start to wrap up and talk about what are the contributions and what is the future work for Do-PFN. So our contribution is kind of being part of the first wave of using the PFN paradigm for causal effect estimation. So we propose a model which we call Do-PFN, which assumes no graph knowledge and requires only observational data. We also kind of challenge the normal causal assumptions that are made by causal inference methods, and instead we shift our assumptions to basically the belief in our prior. We also show that we have well-calibrated uncertainty under non-identifiability, and we also show strong and kind of surprisingly strong performance given our simple prior on a wide variety of causal scenarios and also transfer to real-world data. So let's talk also about what the limitations of Do-PFN are. So the prior is really critical, right? We see that the methods that use more expressive models, specifically tab-PFN, which has a more complex prior, can really perform well for causal inference. One can also say, and we sometimes get this reaction, that pre-training is quite expensive. So we pre-train for four days up front, but we should also note that once you've pre-trained, you don't have to run training again for every task. In general, although Arik has done a really good job with the theory, our general understanding of PFNs is still developing. And if you're actually in a setting where you can confidently make causal assumptions, or let's say that you just know the causal graph, Do-PFN might not directly benefit. Although the hope is that we would also be able to provide competitive performance in these scenarios too. So the future work of Do-PFN, better priors, estimating different causal effects, and also being able to simulate all kinds of different interventions, so shift interventions, continuous interventions, multi-node interventions, improving our theoretical understanding of PFNs and PFNs for causal inference. And then another direction that's really cool is kind of incorporating causal assumptions into Do-PFN. So combining this approach with what people are used to. So with that, we wrap up. Thank you very much for your attention. Yeah, as I mentioned, Arik and I will be at NeurIPS and Europe. So if you have any questions, feel free to write us an email. Here's the QR code for the preprint. And yeah, thank you very much, and we look forward to your questions.